So, have you ever wondered if that whole sci-fi dream of quantum teleportation is, actually a reality today? Like, are we really on the brink of beaming complex information instantly across vast distances? Well, buckle up because it is fundamentally changing how the world communicates. Welcome to The Explainer. Today we're taking this incredibly fascinating journey from what sounds like pure physics magic all the way down to the real-world physical hardware that's actively being built right now. We're going to decode the hype, look at the actual science, and see exactly how telecom giants are paving the way for a totally new internet. All right, let's dive right into this. To make sure everything is crystal clear, we've broken it down into 5 steps. We'll start with the quantum network revolution, then look at the strange rules of quantum, encoding the unseen, real-world quantum teleportation, and finally, Cisco's quantum leap. Okay, part 1, the quantum network revolution, scaling out the future. So right now, the massive race in computing is to build bigger, more powerful quantum computers, right? But just like the early days of mainframes back in the 1960s, you can really only scale up so much. Eventually, you absolutely have to scale out. You need a network. We aren't just scaling up quantum computers, we need networks to connect them for just unbelievable distributed processing power. We're talking about unhackable security through quantum key distribution, supercharging ridiculously complex medical and environmental simulations, and completely upgrading distributed sensing equipment. To put the sheer power of this into perspective, just consider this single number: 9. In a recent real-world simulation, IBM actually worked with a customer to predict anomalous weather events using quantum computing. And get this, they were able to accurately predict hurricane landings 9 hours earlier than the absolute best supercomputers we have available today. 9 hours! Think about the massive difference a head start like that makes for saving lives and property. It's a real game changer. And if you want to see the power of simply upgrading the network itself, well, just look at this data. Over in Australia, there's this incredible deep space telescope array made up of 36 parabolic dishes. If you interconnect them with a standard classical digital network, their margin of error sits around 16.7%. But, and this is the wild part, if you leave the physical telescopes exactly as they are, don't touch them, and only upgrade the network interconnecting their signals to a quantum network, that margin of error plummets down to 2.78%. That is a massive quadratic leap forward in our ability to peer into deep space, literally just by changing the network. Moving on to part 2, the strange rules of quantum, the physics governing the network. All right, first things first, we need to bust a pretty massive pop-sci myth. You've probably heard the media claim that a quantum bit, or a qubit, exists as a 0 and a 1 at the exact same time. Honestly, that's confusing and kind of paradoxical. Instead, I want you to think of superposition like a spinning coin tossing through the air. At any given split second, it isn't heads and tails simultaneously, right? It just has this constantly changing probability of landing on one or the other. And the exact moment you catch it to take a look, boom, that probability collapses into a single permanent state. Now then there's entanglement. This is the mind-bending idea that two particles can be permanently linked, so if one changes state, the other does instantaneously, no matter how far apart they are. Back in 1935, Albert Einstein was incredibly skeptical of this. He famously called it spooky action at a distance, figuring there had to be some hidden local variables we just couldn't see. But skip ahead to the 1960s, and mathematician John Bell drops a theorem arguing Einstein was actually wrong. And it wasn't even until 2022, just a couple of years ago, that the Nobel Prize in Physics went to scientists who experimentally proved Einstein's skepticism was totally incorrect. So yeah, entanglement is absolutely real, and it completely defies our classical understanding of reality. Which brings us to another fundamental rule, the No-Cloning Theorem. This dictates that it is mathematically impossible to copy an unknown quantum state. Why? Well, because to copy it, you have to read it first. And as we literally just talked about with the spinning coin, the moment you read or measure a quantum state, it collapses. The original data is completely destroyed. Now, if you're in cybersecurity, this is amazing because hackers literally cannot copy your encryption key without destroying it and tripping the alarm. But if you're a network engineer, it's a huge headache. In traditional networking, we boost fading signals by reading them and pumping out amplified copies. In the quantum world, we are strictly forbidden from doing that. Okay, part 3, encoding the unseen, moving quantum data. So quantum computers generally rely on electrons to do the actual computing. But electrons are incredibly fragile little things. They have to be supercooled down to minus 272 degrees Celsius, wrapped in massive physical shielding, just to keep random heat or vibrations from wrecking their quantum state. Obviously, you can't build a global internet if every single inch of cable needs to be bathed in liquid nitrogen. That is exactly why the networking side relies on photons, particles of light. Photons operate flawlessly at normal room temperature, and they travel perfectly over the exact same fiber optic glass that's already buried under our streets right now. So we're sending light, but how in the world do we actually encode a 0 or a 1 into a single, solitary photon? Well, there are 4 primary ways to do it. First, you've got polarization, which tracks the vibrational direction of the light. Then there's path or spatial encoding, which uses beam splitters. Third is time bin encoding, relying on incredibly precise arrival times. Actually, time bin is brilliant for fiber optics because if a buried cable bends or flexes, the timing stays stable. And finally, there's frequency bin, which simply put, just uses different colors of light to encode the data. Let's step into part 4, real-world quantum teleportation, beating signal loss. Now, remember our big problem from earlier? Signals fade over distance, and thanks to the No-Cloning Theorem, we can't just copy them to boost them. So how do we beat that signal loss? The answer is teleportation. And here is exactly how it works, step by step. Let's say Alice wants to send Bob a pristine quantum bit. Step 1. Alice and Bob establish a blank carrier pair of entangled photons between them. Step 2. Alice takes the actual target qubit she wants to transmit, and she entangles it with her half of that blank carrier pair. Step 3. Alice performs what's known as a Bell state measurement. Now this is key. She intentionally doesn't measure the target bit itself because that would destroy it. She only measures the interaction between the bits. And finally, step 4. She takes the resulting classical data from that measurement, which is essentially just the noise generated by the entanglement, and she sends that noise over a normal, everyday classical network to Bob. Bob then applies that noise correction to his photon and perfectly recreates the original target qubit without anyone ever having actually read it. It's like magic, but it's math. All right, we need to vigorously bust another huge myth right here. Does quantum teleportation transmit information faster than light? Absolutely, 100% no, it doesn't. While that entanglement reaction between Alice and Bob happens instantaneously, remember step 4, Alice still has to send Bob the classical correction data so he actually knows how to untangle the noise. And because that specific correction key has to travel over a standard classical network, the transfer of any actual usable information is strictly bound by the speed of light. To make all of this practical across a large-scale network, we use something called entanglement switching. So instead of Alice needing a direct, physical fiber cable connecting her directly to Bob, a central device generates the entangled pair and shoots the photons out to both endpoints. Think of it exactly like a classical top-of-rock switch in a data center. It connects multiple devices effortlessly without needing a messy web of direct point-to-point links between every single computer on the network. And that brings us to part 5, Cisco's quantum leap, hardware in the real world. So just recently, Cisco achieved a massive breakthrough in this space. We're talking 500 entanglement swaps per second, sustained over 17.6 kilometers. And honestly, the best part? They didn't pull this off in some sterile, perfectly controlled university lab. They did it over existing commercial fiber optic cables, buried right beneath the busy streets of New York City. This whole field is rapidly leaving the whiteboard and entering physical reality. Just look at the tangible hardware milestones Cisco is putting out there. They've built quantum random number generators. They've engineered a teleportation chip that successfully operates at room temperature while barely sipping any power. And, probably most impressively, they've introduced the world's very first universal quantum switch. The defining feature of that universal quantum switch is that it's fully multimodal. Remember those 4 different photon encoding methods we discussed a few minutes ago? Well, Cisco built a flexible switch that doesn't force engineers to just pick one and get locked in. It can receive and interoperate with any of those encoding methods, all in incredibly high fidelity. It perfectly echoes the foundational networking philosophy that made the original internet thrive in the first place, Build flexible infrastructure that speaks everybody's language. Now, before we wrap up, we do need one final myth bust. The idea of a pure quantum network coming in and completely replacing all our current internet infrastructure, total myth. The math itself literally dictates that you cannot control quantum teleportation states without sending classical correction data right alongside it. So the reality is a hybrid classical quantum network. Quantum isn't replacing classical networks, it's just augmenting them into this unbelievable hybrid powerhouse. The fiber optic digital networks we rely on today are always going to be required to support the quantum links of tomorrow. Which leaves us with a pretty profound thought to end on. We are actively watching the foundation being laid for an entirely new era of human connectivity, one that's built on probabilities, actual teleportation, and unbreakable physics. So I'll leave you with this. As this technology scales out of the lab and into the streets, how will a hybrid quantum classical internet change your digital reality tomorrow? Keep learning, keep exploring, and I'll see you in the next explainer.